we were talking about networks that can eat sets, and maybe sets with additional structure. Well, basically the three ways we do this. The first one is just to take it back, just sum everything in the set. The second way is attention, and the third way we'll talk about is graph networks. So now we'll talk about attention. So attention is going to be bags with weight, rather than just bags, and the weight is going to be dynamic. Attention is going to be a sequential way of processing the sets. So the graph network, the last thing will be a kind of parallel way of processing the sets. Okay, so attention is kind of a thing now, a lot of people are looking at. And when we're not talking about bags or kind of specifically with sets, attention, well, what it means some sort of linear distribution on the inputs. So we want attention to be dynamic, so attention means a weighting or distribution over inputs that is kind of depends on some state and depends on the inputs. So attention in vision has kind of a pretty long history that I know that I've kind of watched happily. So there's long been this thing in vision. Well, humans use saccades, so your eye jumps around. So even at the kind of lowest scale of vision granularity, you don't see like a big thing, right? You don't see everything at once. You see little tiny things, and your brain moves them together. And so, well, and of course, you also focus on things at higher scales, but in particular, at kind of the very lowest perceptual scale, you're really using attention. And so people try to do, well, humans do it, maybe we should do it as well. And so I wrote, this is the other thing you can find. I'm sure people have talked about it since long before then. I just traced a few papers back. But the basic idea of, well, everything in this list and lots of papers that didn't make it in this list is we're going to look at some place in an image. I'm going to take a little square. We'll see what's there. We will update our hidden state, and with that new hidden state, we'll look somewhere else. You'll take whatever's in that, in that square, process it, and look somewhere else, and so forth. It's important that you have. The thing about computer vision is that you have images, and you have a notion of looking at squares in the image. So this is attention over the grid, and you have really a specific shape that you're looking over. So actually looking back at all these, it's kind of surprising how modern some of these look, even if they weren't successful. Like this one is using reinforcement learning inside the machine. So it's not it's not kind of, I guess, modern reinforcement learning, but these guys are using pulse gradient to decide which ones they're going to do next. I don't know, it's kind of modern. Anyway, okay, so attention also has a pretty long history in NLP, but as far as I can tell, so I don't know this literature as well, but as far as I can tell, the attention is called alignment. And there's lots and lots and lots of papers that talk about alignment and the context of machine translation. So alignment is, you have language 1 and language 2, and you want to find kind of the ordering of the source language so it matches up with the target language. And of course, you don't have a ordering of the source language so it matches with the target language. You have lots of possible orderings, right? And so you have some probability distribution over orderings of the source so it matches the target. And there's, since there's a lot of them, this zero probability distribution, it actually fits the kind of definition of attention we had before. It's a weighting over your inputs, given the condition on your current state and your inputs. So it also, but it feels a little bit different than kind of what I was talking about in the previous slide with vision, because it's not attention in the sense of focus, it's attention and the sense of something to optimize over to get a match, right? So as far as I know, again, I feel like that don't know where this is, as far as I know, the first place where they did attention is focusing is the Levin paper, which is pretty recent. And that paper, I think, is the one that kind of restarted the attention phrase. So, what we're going to talk about here is attention on bags, not kind of generic attention. We don't need attention alignment, we need dynamically weighted bags. So, someone's going to give you a bag, someone's going to give you a set of vectors, and you're going to output a weighted sum of the vectors. And what's important is C depends on your state and maybe the inverse. So, standard approach, if you want to push gradients, is to use a softmax. So you'll get these weights that are softmax of your inner product of your state with, that should be a V, not a C. So that's curiously self-referential formula that is not supposed to be. This is not supposed to be recursion. So C is supposed to depend on V here. Sorry about that. So yeah, so the attention on the ith input of the set is supposed to be a softmax over the inner product of your kind of current hidden state, your machine's current hidden state, and vector. And another way of doing the same thing, well, not the same thing, is to use kind of hard attention. So I guess in some extreme cases, like softmax, but you literally just say, I'm going to look at one of my S objects, and again, that's supposed to be a V, not C. So this thing again is just a weighting of the bags, and that weighting of the bags is dynamic. So it's kind of cool because attention is a generic computation method. It allows you to do really crazy things with sets. But anytime someone says you should be interested in this because it's generic and it allows you to do really crazy things, then I mean you should be very suspicious because generic means not good for your problem. It doesn't mean generic is usually a center run away. So why do you care about attention? So I mean you might actually care about this as well, but really in terms of right now what you can do with attention. So if you have something, for example, a sequence which is very long, and you want to run something on a sequence which is very long, it's hard to get gradients going all the way through the sequence. In some sense, the statement that we care about things that are very, very far apart in a sequence means that actually the data is not structured like a sequence, even though it has an ordering and it's maybe on a grid or something like that. You're choosing to ignore that order. And so to some extent, we should look at it as a set instead of a sequence. And this can help, potentially helps with that, because instead of having to push gradient through a million steps to get this fact over here, you just have attention over the set, and you only have to make one step. So it deals clearly with sparse inputs, because we only look at some of those sparse inputs at a time. And this last one, I think, is particularly important. Again, deep learning tools sometimes need to admit things like this, but this last thing is super important. Attention allows you to inject domain knowledge into your machines. In other words, for example, the idea is that we can choose the rules that allow you to step from one attention of one step to attention of another, and we can choose those kind of dynamically at test time, but we can use domain knowledge to do it, or we can choose the kind of set of things we're going to look at dynamically at test time, and we can use domain knowledge to decide what things are going to be in the set that we're going to attention over. So this kind of attention to the bag seems to be, I mean, I'm sure everybody did it in the 90s, I don't know, but there's been a kind of renewed focus recently. Let me put a line between these two and this one, or these two bullets on this one. I think this paper generated kind of began a lot of interest. We kind of got thinking about it. But this one is similar in some ways to the original, where we have kind of a window. So you have attention over a window, and it was, so I was very close to the paper where you have an RNN generating handwriting and look at a chunk of space when you're going to decide where you're going to go. But this one this paper that I is the one that kind of really kicked it off, and that's content-based, and that's what we're going to do, where deciding where you want to look in the text is based on the embeddings of the words in that text. And it was in the context of translation. And then there were, the memory network paper by Weston and the neural machine paper by Hans Brave, and World had a paper of the memory network. So it's really started to kind of be a thing now. And the point is, in these papers, you decide where you want to attend in your set by content plus location. And what does plus location mean? It means that you add features to your set, saying this vector in my set has a spatial location and it has its content. So in some sense, I can remove this word just say our content because you've added information and features, but you really have what's called an associative memory. You are looking at things based on what's inside. And again, that came from here, but in a more general context. Starting in okay, so let me skip this. So I'm going to talk specifically about memory networks. It's, I guess, the version of attention that we use a lot on Facebook. The initial paper was by Jason Weston, and Ward. And so what happens is you input a vector, you input some initial vector, and you input a set of vectors, and the network eats the first vector, gets an internal state, and then operates by kind of hopping over the backwards. Operates by hopping over the set. So again, each update to his state is like I showed before, and then it's just a set of vectors. And this thing is at least now fully backhoppable. So what does it look like in pictures? You start with something that looks like this. So these are your set of vectors. And you start with some state. You take that product between this guy and these guys. You push it through the softmax. You multiply that softmax by these. Get a weighted sum out, and that's what updates your kind of state. So in sequence like this, you decide on a number of hops in advance. By the way, Alex Graves has a new paper about what to do if you want to fix the number of hops in advance. And actually, Jason, in his original memory paper, has this thing as well, where you can kind of output a stop symbol. You don't have to fix the number of hops if you really don't want to. But, okay, so you fix the number of hops, the number of times you want to look at your set. You input the things that you're going to have in the set. Now, this line here is, again, a really important place where I can use domain knowledge. Because given my input, so here I can input M, but I might have some other inputs, and I might decide using my other inputs how I'm going to get these M. So, again, what you do is you take the inner product of your current state with all the memories. That gives you these weights. You update your hidden state with the sum of the weights, and then you go back and do it a bunch of times. And after you've done it a few times, you can update that hidden state, or you can process some other machine. So again, large-scale architecture is you have some input internal state, and you do several hops of this, of the kind of slide that we had 2 ago, where you have attention over this, you make some of it, you output the new hidden state, or you add to the hidden state, and you repeat a bunch of times. So it's sequential processing of a set of objects. So yeah, we should just.
I have a question just to try to sharpen a bit my intuition. So here, you see this as a block that takes a set of input vectors. So
yes.
This is your set representation. And the thing that you really want to get out of this block is a hidden state.
Yes.
That is like some nonlinear summary of the set.
Yes.
And you don't impose any properties that if you, so you have this property that if you permute the input vectors, the output doesn't change.
Yes.
Okay, so that's your generic set transformation somehow.
Yes. So if you'll notice, each of the operations here is conditioned. So let's look at the. So this is a statement about the tension, and again, I feel like we do it because there's supposed to be a B here. But this thing, this soft mask of the inner products, is permutation. That's kind of the building blocks. That's why all the other things are. And then once you have that, if you look at each of these things here, okay, so this is, again, this block is actually the same as that formula. So each step is a permutation there, because you do whatever tension you add up, so that's a permutation there. And then you do multiple steps of that, but each step does as well. So there was no place where
right, and here the number of hops is like how deep this set transformation is somehow.
Yes. That being said, I've written down simplest version here. There's a lot of stuff you can do here as well. If you want to kind of add more depth. There's a lot of transformations you can do on the way, if you want to know that. So, yeah. Okay, so, again, if you remember from last lecture, it's super important that you featureize your data well. Again, this is one of these things that people kind of, sweep under the rug, but it's really important that you featureize data. So I'll give an example in a minute. So here, if someone gives you a set of objects, those objects aren't vectors, or they're not arrays in any way, you need to make them into arrays. And your choice of array, your choice of how you want to build arrays out of them is crucial to make things work. If it's just, for example, words from a finite dictionary, then a lookup table is often a good choice. But then you might want to include a lot more information. This is the same thing as previous slides, it's more complicated. It has the featurization and it has some other stuff. Okay, so yeah, so I guess I was supposed to say this. So again, yeah, the featurization is important. Let me skip. Oh, I want to highlight this. So the featurization is important, and you have to do it as a user. But one important thing is you can always push features back. So if you do a lookup table, you can always push gradients back. So if you do a lookup table, for example, on words, of course this machine gives you gradients all the way back to the lookup table. So the featurization is trainable. Okay, so here's an example of a featurization. This is exactly the one we saw before. So in the last lecture we talked about, well, if someone just gives you words from a set, how do you make vectors out of them? Use that word. Sorry, use a lookup table. So let me show a video again. It'll be easier than trying to. Okay, so here again is the little games that was the last time. Again, it's very hard to see. I apologize for that on the screen, but this here is what. So this is actually being operated by a memory network. Its job is to push the block onto the whatever thing. Oh, it's actually going to change. It's going to go through all that. Anyway, so this is what the network actually sees. So this is featurized as a set of sets. So basically, you get a set for each of these. Each item on the board is represented by several words. Okay, and there are the variable number of words. So the description that the network actually sees before it featurizes is a set of things. Each object in the set corresponds to one of the objects on the board. And then each object in the set is also a set, and that set has all the properties of that object. Again, each object on the board might have a variable number of things, so you have a set of sets. This is very nice in the sense that it's sparse. It's very sparse our representation, but it's also something that we need to featurize, right? So how do we featurize this? Well, for each object, we have some number of words describing the content of that object. So for example, it might be a block that is pushable. So you have something like the word block, and then, pushable. And then you have some words describing its location. So this trait is important, and you see it in a lot of the the recent literature on attention in neural study. This idea that you can append location information to the sets and keep them in sets. So this is kind of crucial in there's these big tasks that were in the original memory network paper where you had to answer questions about really simple dialogues, and part of the information that was put into each sentence is what was the time stamp of that sentence. Here we have an X and Y location as appended. In the Earl's paper you have kind of locations, you have notions of what was the name in a sequence of that object. And it's really important that you put a word corresponding to location information into the set, so that even though you have, into the kind of bag that describes the object, because otherwise you don't know where that object was, because it was in the set. You don't have this notion that the location is where you are in a vector anymore. So when you look at like a comment, or if you look at a sequence, like you get the location by which index did the object have. So once you go to this setting where you want sets, you have to put that into the featurization. So it's slightly different. And then, so for example, in the game I was showing you, in a lot of these examples, you can just go back over these. So one thing to remember is, in the last lecture, we talked about how much space is in RD and what you can recover from backs, right? So if I put all these words describing an object into a back, as long as the word doesn't matter, actually I keep the information about each of those things, even though I'm summing them up. Right? So what we saw last class is that you can sum up a bunch of words, and you can get the information from each of those words back. You don't, just because you sum them up doesn't mean they've disappeared. Each of the words is kept in the sum. Okay. Yeah. So, actually, no, I'm understood. Okay. So there's some places where this sort of stuff works super well, and there's some places where it works less well. But this gives you another example of featurization. So here, let's say we want to use a memory network for VQA, like we saw before in the last class. Yes?
Is there an equal number of the properties that you can have?
Yeah, sure. So, like we saw last class, right? Like we saw last class, like the more things you add together into a single bag, right, the harder it is to get any of those things back. So of course it's going to be blurrier and blurrier and blurrier. If you make one thing into a sum of 1,000 things, you're not going to be able to pick out a lot of those 1,000 things if you're in R20, right? And if you increase the size of the dimension and you're summing everything in, then of course everything gets harder. The lookup table usually has most of your parameters. So the more things you sum, kind of the bigger the dimension of the objects you're going to have to be if you want to keep all of those things separate. And the bigger the dimension, the more parameters your system is going to have, so you're going to need to have a long training data. Okay, so here's another example of how you featurize something. So for example, suppose you take an image and you want to do VQA. So you take your image, you can divide it into lots of little chunks. And then you take the output of a comment at that chunk and maybe the location of that chunk, and that's one thing that you put in memory. And then kind of each of the words in the question, you put it into its own separate location. So you have visual vector, visual vector, visual vector, visual vector, visual vector, visual vector, and each of those things you just kind of put into the set along with its location. and then you put maybe the words of the question word 1, word 2, word 3. So this works in the sense that you get the same, if you just run this naively on the same data, you get about the same as you did with the backboard. So it works in the sense that it trains. It doesn't work in the sense that it wasn't any better than backwards. I mean, the thing is, as I mentioned last lecture, for that particular example, nothing is better than backwards, really, up to 2 or 3%. But that's how you might feedback. So now what I want to do is I want to contrast let's say I want to use this thing for language modeling. I want to contrast the way it looks with how the recurrent sequence, with how RNN for language modeling looks. So if you remember, we talked about RNNs for language modeling. What we do is you have a sequence of words. And you have an output sequence, which is just the input sequence shifted by 1. And if you're kind of a classical LMRN, you get the hidden state as, wow, I switched from H's to S's. Okay, so these are the hidden states here are S's for whatever reason. And so you're let me just look at the old, let me just put the slide from the previous one. So let's look at this one. That's much better. I don't know why. Okay, so you have an input sequence word 1, word not, word 1, word n, and you update the hidden state with some function of the previous hidden state and the previous word, and you update your output with some function of the hidden state. And when you run this thing, you get this random walk business. So you start with some word, you have a distribution over what the next word is going to be, and let's say we've already trained this thing and we're generating, you can sample from that and get the next word, and now you have a distribution over what the next word is going to be, and so on and so forth. Let's contrast this with what a memory network looks like. Okay. So again, this was the kind of traditional RNN viewed as a language model. So you input some, again, a kind of test time when you're generating. So you input some C word, you get a state, you output from the state some distribution over your words, you get a sample and feedback. Memory network has almost the same picture. But what happens is you take your input word and you have some subset of all the words in the universe that you've put into memory. And what you do is you get a distribution over the words in memory. So instead of getting a sample, instead of getting a distribution over all the words out there, you only get a distribution of the words that are in memory. Right? And you don't sample from it. You keep it as a distribution, and that gets fed back into the machine. And then once it's fed back in the machine, it updates the state, you get a distribution over the words in memory, not all the words. And you have this distribution over all the words in memory, and that updates the state. And then you toss it back in the machine, and then you update the state, and then you have a decoder, and then you actually sample to get it to work. So you have, instead of having one computational step to get it, and in subset, one computational step is a bit of a lie because, for example, the RNN would have been multi-layered, you could call those multiple computational steps. But instead of one can explicit computational steps before you produce an output, something like this has multiple computational steps looking at its memory for things up. So we draw a picture like before. So you get your input word. Now you put some other words into memory, and you get a distribution over those, right? You update the hidden state, and that gives you a new distribution over the words that are in memory. The input word is still fixed, right? Notice that these words are different, and maybe a subset. They could be completely different. This is some subset or some completely different set of things. These are the things that are literally put in memory. So now you get a new distribution over those. And then you get an output distribution, so this is a 2-hop memory network, and then you sample from that. So if you want to follow this equation, it's a little bit, this picture and that picture I showed is a bit flipped. So if we look at this here, you have the internal state, you get this addressing, you get this weighting over the input, that was getting a distribution. And then you take that distribution and you sum it. You go here, and this is where you got the distribution over the memory factors. So what's important is that
So here, how do you optimize the memory?
What do you mean? Like what's put in it?
Yeah.
You don't. So that is, if you'll notice, I said there's a place where a user gets to decide like how to put domain knowledge in, and that is the place. So which things get put in memory is something that you decide, and it can and should be dynamic, but it isn't something which is trained. It's something which you as a user decide and do. So let me give an example. So one thing that you can use memory networks for, that we try and use memory networks for, is dialogue. We want to try and pretend to do a dialogue, and we want to do it by retrieval. So a simple thing to do is you have a giant corpus of dialogue, and you say, okay, here's the last few exchanges. Here's the last few exchanges. So maybe you have like 5 exchanges, and then you have your gigantic corpus of dialogue. That's not your current dialogue. What I can do is say, well, here's the last 5 things, and look at all the keywords here, and I'll do some TF-ID and look up everything that's over there, and I'll pull all the ones that match, and I'll put those in memory. Right? And that actually that's pretty effective. So that was in the SLR maybe that we just had. It's super effective for pulling chunks of text using TF-IDF, and then those go in memory, and then you look carefully over them. So this coarse search that lets you decide what you're going to put in memory, it's not trained.
So is it fair to say that this is like a sort of a deep version of this template matching? So when you do like kernel, you have a bunch of exemplars,
Yes.
and you kernelize, so you just replace your information as to like a bunch of products from.
Right. So the reason it's different is template. Sorry.
Please repeat the question.
Yeah. So he asked, is this like a deep version of template matching? And the answer to that question is no, it's actually quite different than template matching because it's sequential. So each time you look at a template, so it is template matching in the sense that you take, so it's, you have multiple steps of template matching, right?
Recursive template matching.
Yes, but you're updating your hidden state each time, right? So you have your current hidden state, and you do match your current hidden state against the templates, if you want to think of them that way. But then, after you've done that, you push a sum through that updates your hidden state, and now your hidden state is different, and now you're going to go match against the templates as well, again, to get the next update, right? And so each computational step actually has a completely different hidden state. So what you're looking for, like what template you're trying to match, is different in each computation step.
So what is it doing more powerful than? So what is your intuition on the utility of having several hops? Let's say, what is the difference between having 2 hops and 4 hops?
Okay, so the easiest, I think, examples of that are the baby tasks. Like those, I think, very close. Maybe, okay, so let me pull the paper and I'll show you what the hops look like on the baby task. And then we'll take a break, okay? So let's Okay, so if you look at this guy here, right? It's a little square. And so the way this is going to be featureized when it puts into a memory network is this is going to be one memory, and it's going to be a sum of these, and then the time. And then you have one memory here, and it's going to be added, and you'll have the time, where the time added. Okay? And so the story is Sam walks to the kitchen, Sam picks up the apple, Sam walks into the bedroom, Sam drops the apple, where's the apple? So if you only have one hop, all you can do is say, where is the apple? So you have Sam drops the apple, Sam picks up an apple. So where's the apple? There's no way to find out, right? You need one more computational step to figure out where the apple is, because you need to go find where Sam was. Right? So the number of computation steps allows you to take, oh, this is an item of interest, now I need to take, so I noticed this word apple is important in the question, now I'm going to go through my memories and find where's the apple, and I will allow those bits where I saw apple to update my hint state, and now that tells me a new thing that's important. And I'm going to go look for that in the memories. Right? So that multi-step thing is actually really, really important. So as an example here, if you look at kind of the original motivation for the memory network paper, what Jason and everyone were trying to do is they wanted to interrogate knowledge bases. And each hop in memory is kind of like a step. It's like searching over the knowledge base graph. So there's lots of questions that are 2-hop questions.
So is it more like a distance in some abstract graph?
Yes.
That connects like questions and answers?
Yes.
So, okay.
That's one version. I mean, it turns out that there's lots of reasons why you might want to do hops. But yes, that's why. Okay, so now it's 10:30, so I guess let me take a some break. Well, so what do you think is knowledge? The graph is explicit. How close object 1 is to object 2 is what relation is that loss of graph. And what the memory network says, okay, how close is the same thing, right? But you're expected to make that step. Okay, so you think that as a low memory network, they might find a representation that is within that. Yes. So, except that you may really want this. Like you say that, so you say, oh, this is helping on graph. You'd like to do it. I skipped that slide actually. I was going to say that. Yeah. And actually, yeah. Look at. If you look at this, you never sample this when you're doing the memory space, right? That's mushy. Each step is mushy. Right? If the thing gets blurry, except that being said, so watch this. This is something so this is the words, right? That's positive. and you try to do this thing. In fact, it's very deep. It alternates between looking at the last few words and then looking at the whole bag as a sum. And then it updates the state and then looks at the last few things. Actually, when we do this, it does it every time. It gets, you get this big blur over everything, and then you get like a tiny little thing. So it can decide blurry at one hop, and then be super sharp at the next hop. Like there's nothing stopping it, especially if you remember this.
Yeah, I think I missed it. It's not normal. I tried
So the hidden state gets updated by this, right? So even if that's blurry, based on what he said, is that the next step? You spike the strip out. You don't have to. So actually, so if you want to think about, I mean, okay, so for small data, getting something again, it's very hard to find. Apple should be right? So on the first hop, and then the second hop, Joe should match Joe. So there's some situations where having that with ice is important. Generically, no. And if you have enough data, and you have kind of good trainers, it can be What do you mean? So it's sequential. So I'll show you examples where this is not. But yeah, it is actually really cool how generic it is. But you could imagine going through parallel and then shouting across. I mean, yes and no. It might be hard. It might take 30 times. Well, there's lots of things where the search might be big. It might be annoying. You really might need 30 hops because you have to. Each person has to talk. You have to look at each memory in the right sequence, right?
Yeah, so for me, then it looks like more particular, like scaling and particular.
And scaling is important.
Okay.
I mean, so I think you can represent a lot of things like this, but practically it's useful. You don't want 50 hops. You can back up to 50,
Exactly. You want to parallel like one person.
Yes, exactly. Yes, exactly. So that
They do. They did. Avoid the terrorist speech. I guess.
It's because we discussed plans of like destroying the
Okay, so I'll try to go over. So I think we can do the last part pretty fast. Okay, so what we saw was a memory network, which is a form of sequential processing on sets. You get your input, and you kind of you look at the set a bunch of times, and you take a weighted average of the things in the set to get your hidden state, and then you repeat that process a bunch of times to get your hidden state. So it's a fundamentally sequential process. So now I want to talk about something which is fundamentally a parallel version of the same thing. So it's a graphical network. So graphical networks, well, we'll say this. So first, let's just fix the notation. You have a set of vertices and a set of edges, right? And you can use a weighted graph, but it doesn't matter. Everything works the same. And so again, just fix the notation. If I say a function from the vertices of a graph to RD, it literally just means a set of vectors in RD that are indexed by the vertices of the graph, right? There's no difference between those two. What a graphical network does is it inputs a set of functions from vertices of the graph to RD and the graph. So it takes two pieces of information, the graph structure and the function from the vertices to RD. And then the network eats those two things and then outputs a new set of functions from the vertices to RD. And actually, you can make it more complicated than that way if you want. You could have a sequence of graphs and a function from the first one to RD, and you can, at each computational step, change the graph if you really want to, very fancy. So the GNN framework. So this is actually this paper from 2009. Actually, these guys who were doing the GNN, they actually have a sequence of many papers going back to 2006 or further with this framework. And so again, it's this notion that it takes in as input a graph, so a common control graph, and a set of functions from the common control graph to RD, which again is literally just a set indexed by the vertices, a set of vectors in RD indexed by the graph vertices. And so in these guys' papers, what they did is they assumed certain things of contractions, and they kind of let things relax on the graph. These guys don't don't worry if I'm just saying some words. I'm going to explain those. I'm going to say it in a different way anyway. So this is kind of a pretty old thing, but it's pretty cool, and I think we should use it more. So let's say that again, we start with a function from the edges of the graph to our b, and we're going to now update the states like this. The hidden state at the next time step at the j vertex is going to be some function of the hidden state at the j vertex from the previous step, and some communication vector, which tells you what your neighborhood nodes have said. And then you update the communication vector to be the average of the hidden states that the nodes connected to. You can think this for current, it doesn't matter. So this is the kind of iterations that describe what the graph network actually does. So let's make a simple version of it, right? So here, what we're going to do is to show how the graph network works. We're going to show how it operates if the graph is the fully connected graph. Yes?
So do you still have distinction between like the controller and the memory, or is everything controller and memory?
I think in this case, everything is controller and memory, if you want. So, I mean, you can think of, yeah, so in more complicated versions of this, you can actually make, depending on how you arrange the things, you can actually make distinctions. But in the formulas I'm going to show you, I don't think it's obvious that there's a distinction. So I'm going to give a really kind of simple example, and it still looks messy here, but let me expand it out. And then it'll be settled. So let's write the formulas down, and promise the formula will become slightly better. And so the point is that we're going to work on a fully connected graph, essentially. So it's very boring. It's not an interesting graph, but the architecture, even in this setting where you're working on a fully connected graph, is still super interesting. So there, you're given this input set of vectors, right? So this is your input vector. So again, as before, it's always your responsibility to get vectors for your data somehow. But we have matrices HI and CI, and we're just going to make the ith processing step to be non-linearity of the ith h times the ith hidden state, and then again for the c's, right? So this tells you how do I update the hidden state over the jth node. So this is the hidden state over the jth node. How do I update it to the address one step? Well, really simply, it's one layer neural network. And then, again, since this is a kind of fully connected graph, the communication vector is the average of everybody else's hidden state. So now we fix the notation H and C, those are the things there, and then C bar, we'll just call this CI. Then actually, if you look at what the graph network is doing, it's just a plain, fully connected network, right? Where the transition, where the weight matrix at each step has this block structure. It's H is on the diagonal, so H tells you how I interact with myself. So how does the hidden state at a node interact with itself? And C tells you how does the hidden state at a node interact with all the other nodes. And there's a C bar here because I want this to scale with the size. So again, if we look at these two equations, I'm being kind of a jerk about notation. So here, I said I have a set of vectors, and here when I said I'm going to apply it, I'm applying to the concatenation. So it's some slight nuance, but whatever. So when I look at this thing here, right? When I look at this set of equations or this set of equations, it completely, in this setting where I was working on flipping things, it completely falls down to a plain feed-forward neural network with weight matrices see that I have the structure. And again, the C is 1 over n, the C bar is 1 over n of the C, and n was the number of things in the is the number of vertices on the graph. So the cool thing about this, so first of all, this is just a plain feed-forward neural network, which I said was bad, right? But it's not bad because it doesn't matter if condition neural, right? If I switch the order of the graph, all the C's swap around, but H stays the same. Like, independent of where you are, independent of what order you pick, yourself is still yourself, right? And independent of, and then these guys flip around with order. The second thing is, if I make the set bigger, then C bar becomes, you just change the thing you're doing. So this is a feed-forward neural network, except because you have this block structure, it's a dynamically scalable matrix, right? I can make it bigger or smaller without losing anything. So note that this dynamically was as an input, and the permutation event, and you have this. And so this is the key idea. I think this is, if you look at the graphical network papers, and if you look at kind of the more recent ones like the Dylan's group that was an SLR, these are, I think there's a really simple idea that's powering this. And I think it's an incredible idea. Like I think it's important. I mean, I haven't been using that. That usually when we make a neural network, we have a bunch of, we have a vector with a bunch of indices. And we decide index I in the vector is going to be connected to index j at the next level by the weight wij, right? We connect things by index. So in some sense, the fundamental idea here is connect by type rather than by index. So you specify indices have a certain type. In some sense, vertices on the graph have a certain type. And the connections are determined by the type, not the index. And that means it's dynamically, the index doesn't matter. It only matters what types are there. So in this fully connected version, there are only 2 types, myself and not myself. So I'm connected to myself by H connections, and I'm connected to not myself by C bar connections. And again, this is completely dynamically scalable. It doesn't matter what's here. So now I'm going to show a video that Sundar made. I have this somewhere queued up. Okay, so what we're going to do is, so what we have is cars in traffic. Okay, now they're all crashing because they haven't been trained. So what we're going to do is train this thing so the cars don't crash. And so the way this is, each of them has a path that has to go on. And so now we're going to go and notice there's no crash. When there's a little blob over it, that one's breaking. So each of these cars corresponds to a node in the graph. In this case, it's fully connected. And you do several processing steps. You do puzzles. So let's say what puzzles for a second to say what the things are. So each car is a node in the graph, right? And the hidden state over that car is its state on the roll. And what happens is we follow exactly these equations. We follow exactly these equations. We just have a neural network that is feed-forward, except it has this dynamic sizing property and this kind of condition property. So each car has its own hidden state, and to do a processing step, you update its hidden state with each time its hidden state plus the average of everybody else's hidden state transformed by C bar. And then you apply some nonlinearity, you apply this multiple times. Actually, life is a little bit more complicated. The model is slightly more complicated, but roughly it's this. And that tells this car where to go. Now, in this particular example, give me 1 second, I'll get in 5 seconds. In this particular example, each car, it doesn't actually choose exactly where it's going to drive. Each car is on a rail. So there's all the possible paths have been encoded, and each car is assigned to a path. And it doesn't have a choice about which path it goes on. It just has a choice of, am I going to step on the gas or step on the brake? Right? So each car only has a choice. And the reason we did that is because it was super hard to get cars to not just jump out of the way of each other. You have to really be, we didn't want to program car physics, and if you don't program car physics, then if you train them to not crash, they just, cars coming, they'll just go wham, and jump away. That's not easy. So they're all on rails to force them to think about not crashing. So they're all on rails, and they can step on the gas or not step on the gas. But the thing is, they have very limited visibility. I think in this example, each car can see about this photo. Right? So they have to communicate in order to not. Okay, so yes.
Yes, so I'm confused if you can get back to your question. So I see this not only as a permutation environment, but also like kind of input environment. Where do you distinguish between different types of nodes, or like if you have like let's say even two inputs A and B, how do you distinguish that something is N and something is B? Because all these H and C's are the same, right?
Yes, so this is a simple example. So let me repeat the question and make sure I understood it, or repeat it so everybody can hear it. So the question is how do you decide, how do you distinguish between what input type you have? Yeah, so the point is, in this, the graph tells you what the input types are. So remember I said that you're going to input a set of objects, a set of vectors, and a graph structure that tells you what's going to input. The graph tells you what the kind of type structure is. In this particular example, it's very stupid. The graph is fully connected except you don't install it. So you're connected to everybody else. So the point is there are two types. The type is myself, so that gets one trace. And the other type is not myself.
It's just simple case.
Exactly. So for that, for this particular example, it's a really simple thing. But you can imagine much more complicated notions of who I'm going to be connected to. And again, the key idea here is the connection is determined by the edge type, not by the node type, not by the index.
But T is something that you design, you specify. It's like hyperparameter, right? It's not something. It's
The structure in the graph structure.
The matrix T.
Okay, so
The
the
graph structure.
parameters of H are going to be learned, and the parameters of C are going to be learned. But the fact that I only have myself and everybody else's type is given as input. Again, this is one of these things that I think learning people are often allergic to. They say, oh, we want to learn everything from scratch. Actually, it's super useful that we can input the structure as a thing. Now let me show you on this video with the car again. So here we have the video with the car. So actually, here, this thing everybody's showing to everybody. So this is a fully connected graph, like the one shown in the figure. So let's get to the next part. Okay, now this one, actually, once you get a really big environment, right? Once you get this really big environment, actually you can do better than everybody's showing you. This is not fully connected anymore. Right? So here you have a local communication range. And actually that the graph that's input to the system is who are the cars around me. And you only have a small finite range of communication. So the amazing thing here is that graph is dynamic. So if you notice cars are coming into and out of the simulation as this is going, you have one neural network, if you want, that's controlling all the cars, even though some are coming in and some are coming out. It's not like you have one model that's for all the cars that will ever come. Cars come into and out of the control of the network. And at the same time, the communication, like which car is talking to which car is also dynamic. Again, that's input. So we made a rule of what's going to be that communication. That's not learned. The rule is if you're within a certain distance that you communicate, right? But the point is that the network can eat that communication rule and the set of things. Both are dynamic. And you can output an action for every single thing in the thing. So the fact that this is force training, you can see there's loads of collisions actually. So when it lights up, that's when it's breaking. Collisions are like little. Okay. So now after training, they just go. You don't have any collisions. And actually, I'm not sure here, but you can look at the actual language they use. By the way, the thing that's really relevant here, so remember last lecture, I I talked about how much space is there in the sphere. And we saw with the memory networks, oh, this is very useful because we can have kind of bags for each object and still keep all the information from that object. The same thing here. Even though this is kind of a very primitive communication mechanism, in the sense that everybody shouts at each other when it was kind of a fully connected version. Actually, if they all shout to different parts of the RD, you can recover all the shouts back. Each car, by the way, is aware of its own ID and its own location, so you can actually broadcast that in the shout. Right? Of course, that can't scale if you have millions of things. You don't want, again, like the dimension that was required in order to be able to separate things scaled with the number of things shouting. So, of course, if you have a million dimensions, you don't want a million log, number of words embedding vectors. So, for this particular thing, it was important to have some sort of local connectivity, right? If you have a lot of them. But still, you can actually have multiple people shouting on the same channel, and everybody kind of understands it still. And they actually learn to separate out their outputs in space, so that they understand it. Okay, so now so we talked about the full connected here. Let's recall the shape of the graph. So this is just the graph version. So again, the degenerate version is you have your vector over each node of the edge, you have your vector over each node of the graph, and you update with some neural network that inputs the vector over each node of the graph and the communication from the other nodes, and then you update the communication as kind of the sum of the states of the guys connected to it. There's lots of ways. I mean, this isn't the only two set of formulas. Once you kind of have this idea of this is you can do lots and lots of variations. And there's so many problems that you can fix in. For example, the Scarcelli, they did graph matching with this. And I think actually that would be a really good thing to revisit. Just how can you graph matching now compared to before? Because I think probably with kind of today's training methods, and this is actually a very simplified form of how they're doing it. I think you could do this with problems pretty well. There's a lot of problems that you can phrase as I have a set of objects and some connection between them, and I want to observe that, and the set, the connections are something that I tell you at runtime. Okay, so okay, so So now we were supposed to do some. We were supposed to talk about some. I was going to talk about one philosophical thing. I don't know if you want or if you. Okay, so John, I don't know if you guys want, but you'll have to stop for it. So this is kind of orthogonal. So that was kind of the end of the main talk. I just want to say really quickly. So in some sense, this was kind of down there. How to build a model that does some things, and that's cool. And I think it's important to think about models, but kind of from a grander scale, I think there's kind of bigger problems to worry about. And so this is philosophy from here to the end, but it'll only be like 3 slides. So the point is, we don't have a lot of labels, so unsupervised learning is important. I'm not going to try and convince you that unsupervised learning is important. All I'm going to say is we don't have nearly enough labels to do the stuff we want to do. On the other hand, unsupervised learning is hard, and by hard I mean it's impossible. So my boss is big on unsupervised learning. I don't actually think unsupervised learning so my boss is Jan, and I don't know if you've seen Jan in his talks, but he says, I guess this thing with the cake and the cherry, and the cake is unsupervised learning. I actually don't think unsupervised learning is possible without some sort of cherry, without some sort of supervision. You need to know what's important. So the problem is if you've ever tried to do really unsupervised learning, you find that you can actually do pretty well in a lot of cases, and it's irrelevant. You try to learn some statistics about a set, about some data, you actually learn those statistics, and then you apply to some task. And it turns out the statistics you learned had nothing to do with the task that you want to do later, which is annoying. So the point is there's a lot of information. If I think about vision, there's a tremendous amount of energy in the visual signal that is the low pass of the image, right? But the low pass gives you no information about object recognition almost. You can high pass your image, and so all the variance of the data is irrelevant to the actual task of object classification. So if you try to do unsupervised learning, the thing that you're going to pick up on if you're using like symbol L2 as your reconstruction metric is going to be relevant to a task of parallel. So you have these two problems. The details that your unsupervised learner thinks are important can be useless for the task of parallel, and the opposite. The details your unsupervised learner thinks are useless might be important. So weak labels are one possibility. So for example, at Facebook, so by weak labels I mean labels that people made for themselves, not necessarily for you as a learner, and you get them to scale. So for example, there's this great Flickr 100 data set, which has 100 million images, and the tags associated with it. It's really cool, because you can see what you can do with lots and lots of images and lots of labels, but without kind of carefully handling. And I think weak labels are really good, but it's not enough. So two quotes from Leon, engineering AI on fails with different ends. By the way, these quotes are from my memory. I didn't write them down, so they're not exactly correct. Hopefully they get the idea across. And from Rich Sutton, you have this idea that in the beginning of AI, people had kind of very handcuffed problems and handcuffed solutions, these decision trees for those handcuffed problems. And now what we do is we have handcuffed problems, but we use data to train the solution. And what we would like to be doing is having a machine that chooses the problems, so that when it solves those problems, it can do well generically. And I think this is kind of at a large scale the thing that we really need. So let me make this slightly more precise, because people often say, oh, it would be nice if machines were building their own task or whatever. Let me specify exactly what I mean, and then we'll finish. So there's lots of situations that you might imagine where you have a task, you have some notion of supervision, and there's a subtask that would be useful for solving that supertask. If you can specify the subtask in such a way where specifying the subtask takes less parameters than the actual solution to the subtask, you've gained something. So this is the only idea that is less hard to think. So again, if you can find a subtask that takes less parameters to specify than the solution to the subtask, then you're really happy. Because again, what you want is some way to tell you what things in your mass of data are important. And if you can train the subtask using the mass of data, and it took very few parameters to specify the subtask, then you get kind of a gain in the radio amplifier sense. Okay? So if you can design a subtask, and it takes very little, you can use the supervision from above to design the subtask, and then the subtask uses the data to train, and the supervision from above, then, the supervision from the subtask. The subtask is the idea of what's the supervision required. Then you've got something. You managed to take a weak training signal and use it to decide what's important in the training data. Now you've actually used the training data to do the thing. So when people talk about unsupervised learning, there's always this idea of, well, I have all my data, I want to predict all the aspects of my data from the data, right? And this says, well, if you can take very weak supervision and tell you what things in my data are important to predict, then I use my data to train that thing, the predictor. And if it takes less parameters to specify the rules of what's important than it does to train the solution to predict the thing of what to predict those things, then you've gotten gain. And if you do this over and over and over, you get this really nice multi-scale thing. And so I know, so lots and lots of people talk about hierarchical learning. And in some sense, the important idea is, can I specify the subtask with less information than it takes to solve the subtask? So I think being able to do any of these things, like being able to do any sort of hierarchical learning where I take my task and very, very weak supervision and find subtasks, and if I find a subtask and find a rule for supervising the subtask so that the solution to that subtask is useful for the supertask, that's somehow the most important problem. And then in order to do that, actually, so part of the problem is that our tasks are, if you saw from BQA before, the tasks somehow fight you in this. The task, the way we usually decide whether we've done a good job or not, really is built on the head of the data, and we care about all the details. But it's hard to build those things. So, okay, I'll stop.
That's
I have a question. When you say you take a subtask and you try and serve everyone within yes, from another task, don't you think most of the time you get some bias in the subtask to them and so
So hopefully the bias.
Because you get a bias towards team.
Yes, that's the whole point. So the hope is that the labels are biased towards T. So the idea is that if you don't know what you're looking for, there's two. From my perspective, and again, this is opinion and conjecture, but unsupervised learning is super hard because you don't know what you're looking for. It would be nice if you knew what you're looking for, then it would be supervised learning, right? But there aren't enough labels to kind of tell you what to look for. So what you want to do is find a subtask, and again, it's important this notion that it doesn't take a lot of information to specify the subtask. So again, the notion is that there isn't a lot of information in T. So you want to bias yourself to the things that T is important, that T thinks are important, and that's precisely the goal. To make S so that it biases itself towards what T thinks is important. But it still takes all of the data underneath to actually train the solution for us. I don't feel like I answered your question, but
okay. So let's thank Arthur for his lecture. The next lecture is a summary, and it's going to be in the same room as yesterday, at 11:30, I believe.